Hello everyone, welcome to our week 11 Intro to Analysis lecture. This week we are going to continue talking about continuous functions. We're going to look at the extreme value theorem and the intermediate value theorem. We're going to prove some of these results, and we're going to do some applications as well. So without further ado, let's look at Theorem 6.4. So this theorem is going to give us five equivalent characteristics of a function being continuous at a point C. Okay, so if we have a function from our domain A to the real numbers and we have C in A, then the following are equivalent. First one is my function is continuous at C. Okay, and we talked about that this is equivalent to number 2 last time. So the absolute value definition for all epsilon bigger than 0, there's a delta bigger than 0, so that whenever absolute x minus c is less than delta, this implies that absolute f of x minus f of c is less than epsilon. And so, what we can see by using the absolute value properties is if I take this out of the absolute value bars, x minus c, and just applying the properties of absolute value, this says, right, this underlined thing right here, says that x minus c is less than delta greater than negative delta. And if I add c to everybody, this tells us that x is going to live between c minus epsilon and c plus, or c minus delta and c plus delta. Okay, so it lives in the neighborhood centered at C. Okay, so if we draw this picture out, okay, so the neighborhood centered at C, the delta neighborhood centered at C. So here's C and C plus delta, so this is going to be a distance of delta right here. This is C plus delta, this endpoint, and this is C minus delta. And this statement right here is saying that x is going to live somewhere in this neighborhood bounded by c minus delta and c plus delta. Okay, so that's exactly what this is saying. And you can say the same thing here. So again, we're saying, hey, x is in this delta neighborhood centered at C, and that's going to imply that f of x is in the epsilon neighborhood centered at f of C. So, again, if we just use the definition of what absolute value means, just like we did up here, we can say that f of x is less than epsilon plus, or maybe I'll do it this way, f of c plus epsilon greater than f of c minus epsilon. Okay, so pictorially, we have our neighborhood centered at f of c. And then on the right side, the right endpoint is going to be f of c plus epsilon. And the left endpoint is going to be f of c minus epsilon. Okay, so here's my open interval right here. And this is saying, okay, so f of x is going to live somewhere in here in my neighborhood. This is f of x in my neighborhood. Okay, so what does this say? This says that if x is in my delta neighborhood, then f of x is in my epsilon neighborhood. Again, centered at C, centered at f of C. And part 3 is saying exactly this, okay? So it's saying that 2 and 3 are exactly equivalent. It says, you give me an epsilon neighborhood of f of C, no matter how small, and we denote it v sub epsilon of f of C. Well, then there exists a delta neighborhood denoted v sub delta of c, so that whenever x is in this delta neighborhood centered at c, f of x is going to be in the epsilon neighborhood centered at f of c. And we can see that is exactly what we have in our picture here, just from using what it means to be, what it means to take the absolute value. Okay, so those two are equivalent. The next one is, is similar to our functional definition, our sequential characteristic of functional limits. So it says for all sequences a sub n from A which converge to C, we have f of a sub n converging to f of C. Okay, and then finally with 5, we have that the limit as x gets close to C of our function is going to be f of C. We're just going to evaluate the function there. And, you know, you've done this before in calculus classes. You have some kind of like, let's say we have the limit as x goes to 2 of x plus 3. Well, you know how to solve that, right? You just plug in 2 for x and, you know, why do we do this? We're going to talk about this in a few slides, but this is going to be f of 2, right? We just plug in 2 and we get 5. Here's a picture down here of, this is from part 3. So this is the neighborhood sort of definition. So just to reiterate, because I think it's important to think about it like this, because it seems, I mean, maybe another one of these makes more sense to you, but I think that 3 is the most intuitive for me. So anyway, here, instead of C, it's using x naught, so that you can think of this as your C, f of C and C. I couldn't find a picture with C. That's basically it. And so this is saying, okay, I'm going to give you an epsilon neighborhood. That's this gray region. Okay, so the epsilon neighborhood is this gray region, and it's centered at f of C. I give you this epsilon region, and your job is to give me a delta neighborhood centered at C, so that everything in the neighborhood falls into the epsilon neighborhood when you look at f. Okay, and we can see from the picture that this is true. So they give you an epsilon neighborhood, and I give you this delta neighborhood, with the left endpoint being x naught minus delta, the right endpoint being x naught plus delta. And I can see from this picture that indeed every single x in here, when I apply f of x to it, is indeed going to land in my gray region, right? And so that's exactly what this guy is saying. Okay, so those are 5 equivalent ways to look at continuity at a point C. Okay, and so we're gonna do an example here where, you know, like, for 4, it says that the only way your function can be continuous at a point C is that every single sequence that converges to C, when you apply f to that sequence has to converge to f of C. And so the idea here is we can show that a function is not continuous at C by finding 2 sequences which both converge to C, but f of one of those sequences converges to something different from f of the other sequence, right? Limits have to be unique. So that's how we can prove that a function is not continuous at C. And what I just said is written here. So yeah. So let's do an example where we show this. So this is from your book. This is called, depending on, I guess, where you're at in the world, I say Dirichlet. I think maybe Dirichlet is the more, Dirichlet, whatever. Anyway, he was a mathematician, and he has this function named after him. Okay, and it's pretty, you know, it looks pretty innocent looking, right? So f of x is equal to 1 if x is rational, and it equals to 0 if x is irrational. Okay, that's the function. And so what we're gonna get is this picture, right? So remember, the irrationals and the rationals are dense in the reals. So it's like, okay, we have, you know, a bazillion, you know, whatever, uncountably many irrational numbers. And so we're going to have a bunch of zeros, and we're also going to have a bunch of ones because there's uncountably, well, there's countably many, There's countably many rationals. Okay? Uncountably many irrationals. So, how do we prove that this function is nowhere continuous? Okay, so I'm going to just illustrate one specific example of this. We're going to claim that this function is not continuous at c equals 4. Okay, so how do we show that? Well, we can use the neighborhood proof. Okay, so we can see in the picture that that I've given you a random epsilon neighborhood centered at f of 4. Okay, so here's f of 4, and so this is the epsilon neighborhood centered here. And so what you should be able to do, if this were continuous at c equals 4, I give you this epsilon neighborhood in blue. And we should be able to produce a delta neighborhood centered at 4, so that when you apply f to anything in this delta neighborhood, you should end up here. But that's not the case, right? Because of the density of the irrationals and the rationals in the reals, right? Remember what density said. It said that, I can give you a super, super tiny open interval, and there are going to be infinitely many rational numbers in this interval, and also infinitely many irrational numbers in this interval. And so how are we going to do this? Well, we can't, and that's the idea. So the idea here is, I'm going to just write what I have in my notes. So no matter how small your epsilon neighborhood, around C, there will be some x the irrationals in that neighborhood where f of x equals 0. Hence, not in the epsilon neighborhood, right? Because, as I said, there's infinitely many irrationals and rationals in here just because of the density property of rationals and irrationals in R. And because of that, we're going to have some things. So, like, here's an x that's irrational. I'm just drawing it here arbitrarily. It's irrational, and so f of x is going to be 0, right? So it's going to stay here, and it's not going to end up in this neighborhood. All right, so that's the idea. And so you can apply this logic to any c, like any arbitrary c in the real numbers, and we can always say, okay, well, I can make a neighborhood around C as small as I'd like, but guess what? I'm still going to have infinitely many rationals and infinitely many irrationals in that neighborhood. And so there's going to be this jump, right? And remember, the definition says any epsilon neighborhood. You're not in control of epsilon. You could say, okay, but like, what if I made the epsilon neighborhood like this? Well, then everything would fall in. Well, sure, but the definition says that you're not in control of the epsilon neighborhood. I give you the epsilon neighborhood, or, whoever, the god of math gives you the epsilon neighborhood, and you have to find that delta neighborhood that satisfies the conclusion. Okay, so that's the idea. I also want to give you a sequential proof that this thing isn't continuous at 4. Just like, we mentioned here that we can show it's not continuous at 4 if we can produce sequences that converge to 4, but when you apply f, those sequences converge to different things. So, let's look at that. Let me do some erasing. And so now we're going to prove that this isn't continuous at 4 by using, what was it? I think it was 4. Okay, now, so we looked at 3. We showed that it wasn't continuous at 4 using 3. Now let's show it's not continuous at 4 using part 4 of this theorem. Okay. Oh, that Taylor Swift song is stuck in my head. That's so aggravating. I don't know if you guys have heard her new album, but all of the songs are like earworms. It's awful. Okay. Okay. So, all right. So let's use 4 of the previous theorem to show that our Dirichlet function f of x is not continuous at c equals 4. All right, so how are we going to do it? Let's come up with 2 sequences which converge to 4. But when you apply f, those sequences converge to different things. Okay, so like the idea is like, okay, incorporate a sequence that is completely rational that converges to 4. And then find another sequence that is completely irrational and converges to 4. Well, then when we apply f, we're going to get that those things converge to different things because of the rule here. Okay, so suppose a sub n equals 4 minus 1 over n. All right, well, we can see that when n gets large, this thing goes to 4, right? 1 over n goes to 0, so this goes to 4. What does f of a n go to? So f of a n is going to be f of 4 minus 1 over n. And basically what's happening here is like no matter which n I choose, n equals 1, 2, 3, 4, 5, 6, 7, 8, whatever. No matter which n I choose, 4 minus 1 over n is always going to be rational, right? 1 over n is always rational. So 4 minus 1 over n is always rational. And so we know that since this is always rational, this thing's going to converge to 1, right? This is going to converge to 1. But if we look at an irrational sequence that converges to 4, consider b sub n equals 4 minus the square root of 2 over n. This guy converges to 4, certainly, right? If we fix the top, square root of 2, and we make the bottom really large, well, again, this thing is going to go to 0. Okay, so this guy goes to 0, but f of bn is going to be f of 4 minus root 2 over n, and for each n in the naturals, 4 minus the square root of 2 over n will always be irrational. Always, because of the square root of 2. Square root of 2 is always irrational, so square root of 2 divided by anything, any natural number will always be irrational. So we can say that this guy, since this is always irrational, this guy is converging to 0. Okay, so the limit does not exist, right? Because these things go to two different numbers, and by 4, this function is not continuous at c equals 4. And again, you could apply the same logic to any arbitrary c in the real numbers to get that this function is nowhere continuous. So I really, I like this example. I think it's kind of cool. And, you know, if you're into this kind of stuff, these weird counterexamples, there's a bunch of them in the appendices in Cummings' book. And, you know, some of these analyst / just mathematicians in general, like, make their their whole career about finding crazy counterexamples to disprove things. So, yeah, anyway, I think this example is pretty cool. Let's move on. Okay, so this is the same old, right? We have these limit laws. We talked about limit laws of sequences. We talked about limit laws of functional limits. Now we're talking about continuity limit laws, and I'm not going to prove this because it's all the same stuff that we've already looked at before. So, like, you know, we're basically just using the functional limit laws to prove these. So, you know, we're not going to waste our time doing this. But yeah, let's just state them here. So we have a function from A to R, another function, and these functions are both continuous at C. And I think you guys know this from Calc 1 that these are all true. If you have a scalar, or if you have a number in your reals, then k times f of x is going to be continuous at C as well. The sum of those continuous functions are also continuous. The product, and when you divide, that's also continuous, provided that you don't have a 0 in the denominator. Okay. So what I want to do a little bit rigorously is show that, like, whenever you tutor your calculus students, or like whatever, whenever you give them something like this, what do you tell them to do? You say, well, just plug it in. Just plug in 2. And we're going to talk about, you know, why that's a legal thing to do based on our definitions that we have established so far. Okay, so why can we do this? What's the reasoning? Well, last lecture we showed that the function f of x equals x is continuous on the reals. And we all know this from, you know, our life in math. We know that this is continuous. It has no breaks, holes, or anything like that. And let's go ahead and use this hypothesis that this is continuous from what we proved last time to show that any polynomial is continuous on the reals. So what does any arbitrary polynomial look like? It's of the form an x to the n plus an minus 1, x to the n minus 1, and so forth. a1x plus a naught, where, let's say aj, just making j be between 0 and n. Whatever, I'm just saying this in a stupid way, but you get what I'm saying, right? These coefficients have to be real. That's what I'm saying. That's what I'm saying here. So that's what a polynomial looks like. All right. Well, how do we prove it's continuous? Well, we know that x to the n is continuous. Why? Because x is continuous by hypothesis, right? We proved that last time. By hypothesis. And if I keep multiplying x by itself, that's continuous by which property? By this property, right? If I apply x times x, that's continuous. Apply x again, that's continuous, and so forth. So by 3 of corollary 6.2, x times x times x times ... times x n times is continuous. Okay, so that's the first thing, is like, okay, x to the n is continuous for any n. Just using our hypothesis that x was continuous and the fact that you can multiply a continuous function by another continuous function and it's still continuous. Okay? And so, like, so now we have that each of these pieces is continuous. And then we're just going to take for granted that scalars are continuous. If we apply 1 from corollary 6.2, that says that any scalar times a continuous function is continuous. So that tells us that each term, aj, x to the j, is continuous. Okay, so this is just 1. It says, okay, well, now we know that x to the any power is continuous. If I multiply by a scalar, that's also going to be continuous. So each of these pieces is now continuous, right? And finally, sums of continuous functions are continuous. And what is this by? Well, this is by part 2 of corollary 6.2. Okay, so thus any polynomial is continuous on R. Okay, so again, I showed that each of these x to the n's is continuous just by applying repeated multiplication using corollary 6.2. And then I said, okay, well, each of these k times x to the n's is also continuous by applying 1 from corollary 6.2. And finally, since we know each term is continuous, the sum of these terms is going to be continuous by part 2 of corollary 6.2. So we deduce that any polynomial is continuous at R. Okay, so now you can explain to your students why this is true. So why you just plug in a 2 here, okay, to get the limit. Now, we've justified that x to the 3 minus 4x squared plus 1 is continuous everywhere on R. So in particular, it's continuous at c equals 2. Alright, well then by part 5, let's see, here we go. By part 5 of our theorem, because our function is continuous at 2, we can just plug it in. Okay? So yeah, okay. That's it. So that's what you can tell your students. You don't have to tell them that, but maybe when you have real analysis students, you can mention this. So what is this? 8 minus 32 plus 1. I think it's, what is this? Negative 31 plus 8. Negative 23, I think. Okay. Oh, wait. Is that true? What's happening? Not 32. Okay. See, guys, I can't do math. It's actually kind of a problem. I think this is, what is this? So this is 8 minus 16 plus 1. So that's negative 7. My bad. There we go. Okay. So now that we talked about that, let's just briefly mention this theorem. I'm not going to prove it. I think that it makes sense. You've probably seen it in calculus. If you have a function from a to b and another function from b to r, when you take the composition, if these functions are continuous, you take the composition. As long as the composition makes sense, then that composition is going to be continuous. Okay, so let's draw a quick picture of what this theorem is saying. So here we have A, and here we have B and R. Okay, so here's R. So we have G going from A to B. Let's say it's continuous at C in A. So here's C. And if I apply G to it, this is going to be f of C. So it says G is continuous at C, and f is continuous at G of C. Well, f goes from B to R, so we can apply f to f of C, and this is going to be the composition. F composed with G of C. Okay, so it's just saying, okay, if this is G is continuous at C, if f is continuous at f of C, then the composition, f composed with G, is going to be continuous at C as well. So let's look at this definition. So I want to harp on this just a tiny bit because I know it's a little bit confusing. Not all functions have inverses, but we can always look at what's called the pre-image. Okay, and we talked about this a little bit week 1, but I want to go more into detail with this. So like, let me just do this at the bottom of the page. So we know that f of x equals x squared doesn't have an inverse. Doesn't have an inverse. And why is that? Because so let's say that it did, okay? If it did, then if I take the inverse function of something, let's say 4, then this would have to be one number, right? So for inverse functions, like you take in something and you should get something unique, right? But here we know that 2 squared is 4, but also negative 2 squared is also 4. So this is going to equal 2 and negative 2, which, I mean, you don't have one number. You have two things, and so the inverse function doesn't exist. But we can look at pre-images. So what does a pre-image mean? Let's talk about that. So if we have two subsets of the real numbers and a function going from x to y, then for any subset in my target space, so here I'm saying that y is my target space, any subset here, I can pull it back and look at the pre-image of, what is the pre-image of B. Okay, and I know it says F inverse, and I might accidentally say that sometimes, but when you have like a set in here and not an element, you want to get used to saying pre-image of B and not inverse of B. You could say inverse image, but I think that, I don't know, I don't, you can say that, but just know that the function might not actually have an inverse function. So anyway, what's the pre-image of B? That's going to be everything in X, so that when I apply F to X, it lands in B. So again, in this picture, I'm taking the pre-image of B. So I'm taking all of the things that map to B under F, and that's going to be all of this stuff here. Okay, so in my quadratic example, if I was looking at the pre-image, and notice that now I'm not going to put just a number in here, but I'm like thinking of it as a pre-image, so I'm putting a set in here. So if I wanted to look at the pre-image of 4, like saying that f was equal to x squared, well, what maps to 4 under f? That's going to be -2 and 2. That's going to be that set. So like in the picture, that would be this guy, and then 4 would be our set B. Okay, so let's do some examples here. We have f from R to R given by f of x equals 5 of x, and we're given a B, so we're given a subset here of 1, 20, and we want to know what is the pre-image of 120. Okay, so what is the pre-image of the set from 1 to 20? Well, we know that this function is increasing. So here's 5x. I know it's a great picture. We know that this thing is increasing, and so we can, do this like inverse trick, right? Where we say, okay, well, what happens when f of x is 1? What does x have to be? Divide by 5. X is 1 over 5. And then when this thing equals 20, we get 5x, but it's not including it, right? So divide by 5 and get x equals 4. And so here's our set B is going to be from 1 to 20. And so our pre-image is going to be from 1/5 to, let's see. Yeah, I'm not making this the best picture, and it's, it's not drawn to scale, but here's 1 over 5 and here's 4. So this guy would be the pre-image of 120. Okay? And we're not including these points here. All right, let's do this guy. So we have our nice quadratic function, and our B is going to be from 1 to 49. So let's just give a quick sketch. We want to know what the pre-image of B is going to be with this function, x squared. So let's just do a rough sketch here. So here's this guy. Here is our quadratic. And we're interested in going from 1 to 49. Okay, so if I draw out my lines here. Okay, so looking here, I can see that this guy is going to be my endpoint here. This guy is going to be my endpoint here. And then I'm going to look over here at this side. Okay, and so these red pieces are going to be my pre-image. So what is that? Well, that's going to be -7 to -1. Let me just write it like this. And then from 1 to 7. So these intervals map to 149, right? When I apply f to the interval -7 to 1, I'm going to get all of this, right? And then when I apply f to 1, to the open interval from 1 to 7, I'm going to get this. And that's exactly what my B was. Okay, so this is going to be -7 to -1 union 1 to 7. Okay, so let's talk about Theorem 6.6, and we're going to prove the forward direction of this guy. So let's say that we have a function from x to r. Then this theorem says that f is continuous on x if and only if for every open set in the reals B, the pre-image of this open set is going to be A intersect X for some open set A. So we're not necessarily saying that the pre-image is open, because that is going to depend on what your X is to begin with. But we are saying that the pre-image is going to be the intersection of an open set and our ambient space X. So we're going to prove the forward direction. And so we're going to assume that F is continuous on X, and we're going to start with an arbitrary open set B and show that this equality is true where A is open. Okay, so we'll show remember these are sets. Like this pre-image is a set, this is a set, and when we want to show that two sets are equal to each other, we want to show both containments, right? Like the okay, so let me just write it down. We want to show that the pre-image of B is contained in A intersect X, where this guy is open, and that A intersect X is contained in the pre-image of B, where this guy is open. Okay, so this is our goal for what we want to do, and let's go ahead and start with our assumptions. So our assumptions is that F is continuous on X. So suppose F is continuous on X. And what does this say? Well, it says that to deduce this set equality, we better start with an open set B. And suppose B contained in the real numbers is an open set. Okay, so let's go ahead and draw a bit of a picture here just to know what we're working with. Okay, so here's our X, and here's the real numbers, and we have this open set B. So here's B in the real numbers, and we have this function that's going from X to the real numbers. Okay, so what are we going to do first? Well, what can we do? We can look at something. So the idea is that we're going to use continuity to build an open set over here. So what we're going to start with is we're going to start with a point in the pre-image. So let X naught be in the pre-image of B. What does it mean to be in the pre-image of B? Well, it means that then F of X naught lands in B. Okay, so let's just draw our little picture. So here is X naught, and let's say that this guy is my pre-image. Maybe I'll do him in purple. So this is my pre-image of B. And let's say that this is in purple as well. This is B. Okay, so we start with something in the pre-image. Then when I push it through with F, that means that F of X naught is going to be in B. Okay, and so we want to use the fact that B is open and say some things about neighborhoods and use our continuity criteria to deduce something about the pre-image. Okay. All right, so since B is open, what does open mean? Since B is open, well, since B is open, remember what openness means, that there is some neighborhood around every point in the open set that's completely contained in the open set. Okay, that was our definition from chapter 5 when we started talking about open sets. So since B is open, let's call it an epsilon neighborhood. There is some epsilon neighborhood of f of x naught. And let's say that this is just using our notation that we talked about. Let's just say that this is v sub epsilon centered at f of x naught. So that's our neighborhood, which is completely contained in B. Okay, so let's draw a picture here. So this is going to be my neighborhood. This is my epsilon neighborhood centered at f of x naught. Okay, and so now we're going to use the fact that f is continuous at x naught. So f is continuous on all of x, and in particular, f is continuous at x naught. So by part 3 of our theorem that we talked about in the very beginning of the lecture, of theorem 6.4, since f is continuous at x naught, well, remember what that means in terms of neighborhoods. That means that for any epsilon neighborhood you give me that's centered at f of x naught, I can find a delta neighborhood centered at x naught, so that whenever x is in this neighborhood, f of x is going to be in this epsilon neighborhood. Okay, so by theorem 6.4, since f is continuous at x naught, there is some neighborhood, and this is open, right? When I say neighborhood, I mean open set, epsilon neighborhood of x naught. This is an open set. Let's call it v sub delta x naught. So that, and I'm just applying the definition of continuity here by part 3, so that whenever x is in this delta neighborhood centered at x naught, let's say that this is the delta neighborhood, so let me just write it here, delta neighborhood, and maybe I will highlight it here. Here's my in red, and then in blue I have my epsilon neighborhood of f of x naught. Okay, so that whenever x is in this neighborhood, that's going to imply that f of x is in that epsilon neighborhood over to the right. Okay, and what does this imply? Well, this is going to imply that x is in x intersect the delta neighborhood, right? Because if x is somewhere in this neighborhood, it's certainly going to be in the bigger space, right? And it's going to be in the bigger space, and it's going to be in the delta neighborhood. Hence, it's going to be in x intersect the delta neighborhood. Okay, so I'm just using definitions here. All right, I'm just saying this implies this. Okay. And what else did I want to say about this? Okay, so this is going to imply that f of x is in, we already have this, the epsilon neighborhood of f of x naught. And so what does this mean? This means that if f of x is in the epsilon neighborhood, then x is going to be in the pre-image of that epsilon neighborhood. So x is going to be in the pre-image, when I pull it back, of this epsilon neighborhood centered at f of x naught. Okay, and since this neighborhood, this epsilon neighborhood, is completely contained in B, we have that x is in the pre-image of the epsilon neighborhood. Okay, so let's write this out. Since the epsilon neighborhood centered at f of x naught is completely contained in B, when we look in the pre-image, we have that the pre-image, so we have x in pre-image of this neighborhood, and that's going to be completely contained in the pre-image of B. Okay, and therefore we have that our open set A is contained in the pre-image of B. And remember what A is in this case. A was that delta neighborhood centered at x naught. All right, so we have this direction, and by construction, we have that the pre-image is contained in this guy. Okay, and so that direction is shown. The other direction is in the book, but it's definitely not as, I guess, tricky as the forward direction. So anyway, that's the forward direction for this theorem 6.6. So let's take a look at another useful theorem, 6.7. So if we have a continuous function from x to r, and if we have a compact subset of x, A, then the image of A, f of A, is going to be compact. Okay? So let's recall some definitions. So recall from chapter 5. This was 2 weeks ago, I think, that a set A is compact if every open cover of A contains a finite subcover. So what are we trying to show here? We're trying to show that if I give the image of A, so if I do f of A, and I give it an open cover, that it has a finite subcover. Okay, so that is the idea here. All right, so suppose A is compact. We'll show, I'll just write it, what I just said aloud. We'll show that any open cover of f of A has a finite subcover. All right, so what do we need to do? We need to start with an open cover. So let U alpha, so this is a collection of open sets. Let this be an open cover of the image of A. Okay, and so now we can utilize the previous theorem to get some things that we want to prove this theorem. So we have an open cover, and each of these guys is open. All right, so what does the previous theorem say? that if we take the pre-image of each of those open sets, we're going to get something that is open intersecting with X, right? So let's just write that down. By Theorem 6.6, since each of the U alphas is open, we have for each alpha the pre-image of U alpha is going to be equal to this open set V alpha intersect X. Okay, so I'm just saying that this is like acting like our A in the previous theorem. Okay, so let's stop here and draw a picture of what's going on. So let me make this a bit smaller. So here's X, and here is our subset A. So here's A. So we know that A can be covered by finitely many open sets. So this is F. This is the image of, well, this is F of X, so the image when you apply X via F. And so we have this F of A. Maybe it looks like this. And so what we're doing is we have an open cover, right? Infinite. Okay, so like dot, 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 dot. This thing completely covers F of A, infinite, and we want to show that we can condense it into finitely many pieces. All right. So we're going to utilize the fact that A is compact. Okay. So we're going to suppose that we have something in the image. So F of X naught is going to be an F of capital A. All right, so what does that mean? Well, since F of A is covered by the collection of open sets, U alpha, this means that there's gonna be an open set that contains F of X naught. So for some alpha, and here we'll say alpha equals 1, just to make it a little bit simpler, I guess. We have that F of X naught is in U1. Okay, so it's just saying, all right, we have this infinite collection of open sets, and I'm saying that there's a point in the image, and since the image is completely covered with these open sets, that means that this guy, F of X naught, has to be in one of these open sets, and I'm calling this open set U1. Okay, so that's the picture. Okay. All right. So what does that mean in terms of the pre-image? Remember, like the idea here is like we want to relate things to the pre-image because we know that stuff in the pre-image is going to be compact by the compactness of A. So that's the idea. Okay. So let's relate this back to the pre-image. Since this guy is in U1, what does that mean? Well, then X naught, just by definition of pre-image, is going to be in the pre-image of U1. Okay? And so, what does that mean? That means that the infinite collection, so the pre-image of these U alphas, is a cover of A. Right? So, like, you know, you apply the same logic. You say, okay, take anything in the image of A and pull it back to the pre-image, and it's going to be covered by these pre-images of the U alphas. Okay? And notice that, well, what are we noticing here? We have that the pre-image up here, we have the pre-image of each of the U alphas is going to be an open set intersect X. And so we have that the collection of the pre-images of the U alphas is going to be contained in the collection of the V alphas, right? Because this is equal to things in V alpha and X. And so that's what we're going to utilize here. So notice that we have the pre-image of the U alphas completely contained in these open sets, this collection of open sets. And so because these are all open by our assumption, then this collection is an open cover of A. Okay, so now we're in a good position because we know that A is compact, okay? And because A is compact, we can condense these open covers to a finite subcover, all right? So here we go. Since A is compact, this collection of open sets has a finite subcover. Okay, so let's just say it's V1 through Vn. So we're just plucking out finitely many of these, and we say, okay, because A is compact, I only need finitely many of these V's to cover A. Okay, so far so good. All right. So notice that we have pre-image of U1 equals V1 intersect X. Pre-image of U2 is equal to V2 intersect X, etc. All the way up to pre-image of UN is equal to Vn intersect X. And so because of this, and we know that the V1 through N covers A, then these guys are going to have to cover A as well. Okay? So this means that these pre-images will cover A. All right. So we're trying to, so when I take the pre-image, I'm over here, I'm on the left side, and we're trying to bring this to the right side to show that this open cover has a finite subcover. So like what I'm really trying to show is that U1 through UN can actually cover f of A. So from here, what you want to look at is an arbitrary element in the image of f of A and show that it's contained in the union of U1 through UN. And that's just what it means to be covered by U1 through UN. Okay. All right. So so suppose we have something in the image. We want to show that it's covered by finite U1 through UN. Okay, so suppose this is in the image. So what does it mean to be in the image? Then there is an X in A for which f of X equals Y. And since this collection, U1 through UN, covers A, there are some, so since this completely covers A, there's one of these that contains X, okay, right? Because this completely covers A, we know that X is in A, so X has to be in one of these, all right? Let's call it pre-image of U sub K. There is some pre-image UK in this set, which contains X. And so what does this mean? This means that f of x, which is y, is going to be in UK. So we're just playing games here with the image and the pre-image. Okay, well, what does that mean, right? UK, k is going to be 1 through n, right? It's finite, okay? And so what that means is that, you know, we took an arbitrary element in the image of A, and we found that it was contained in the union of a finite subset, or the union of finitely many sets, okay, U1 through UN. So it's in one of those UKs. Okay, so we've just proved the claim, right? So U1 through UN is a finite subcover of the U alphas, and hence f of A is compact. Okay, so that's the proof. So again, you know, we were just leveraging that A was compact and playing games with images and pre-images to deduce that the image of A has to be compact as well. All right, so here is a corollary. A continuous function on a compact set must be bounded. Okay, so notice that this is the function f of x equals 1 over x, and it's continuous, right, from, you know, everywhere except 0. So notice that this function is continuous on the open interval 0, 1. But as we talked about in chapter 5, any open interval is not compact. All closed and bounded intervals are compact. So like 0, 1 would be compact, but the open intervals are not. So there's a problem here. It is not compact. And we can see in the picture, because of the fact that it's not compact, this corollary is not going to apply. And so we can have things that are unbounded on this set, right? And you can see that that's true here. This guy is completely unbounded from 0 to 1. It's just going to grow, you know, it's going to grow without bound. But if we were considering a function on the closed interval 0, 1, well, then it would be bounded, but of course this function isn't continuous at 0, so we can't really use that as an example here. Okay, so that's one corollary of the things that we have, the proofs that we've looked at. Let's move on to our next theorem, the extreme value theorem. Okay, so if we have a continuous function on a compact set, that function is going to attain its supremum and its infimum. Okay, in other words, if we have a function, there's going to be some x values, so that when you apply that function to a1, you're going to get your supremum, and you apply that function to a2, and you're going to get that infimum. Okay, and so the picture, I mean, it's like, I don't know, this is like A to B, and let's say that our, okay, let's say our function is like right here. Okay, so we're including these endpoints, and this, I mean, just by the way I drew it, this is my infimum, well, whatever this value is at f of A. Maybe I should write it up here. This is my infimum, and this is going to be my supremum. And it's just saying that, okay, so A is actually in the set. F of A is going to equal L, and F of B is going to equal M. Okay, so that's the statement of the proof, and let's go ahead and show this is true. So, but now notice that we didn't have a compact set in this situation, and so the extreme value theorem does not hold on 0, 1 for this function because it is 0, 1 isn't compact. And so we can see that it's never gonna, like, there's no supremum here. This thing is gonna go up forever and ever. So it's like f of what is equal to forever and ever. Well, there's no such thing. Okay, so the extreme value theorem only applies to functions on compact sets. All right, so let's go ahead and look at the proof here. So we're assuming that A is compact. So since A is compact, by a previous theorem, 6.7, that we just looked at, this is going to imply that the image under F of A is compact. So applying F to a compact set is going to give me a compact set. And remember what compact means in the real numbers. Closed and bounded is what it means, right? So since the image is compact, it's certainly bounded. Now, if the image is bounded, remember from what we did way back in the day, if we have a bounded set, then it has a supremum, right, by completeness, and an infimum. So by completeness, we know that the supremum and the infimum of the image exist. So the supremum of f of A and infimum of the image. Oh, I think did I put too many parentheses? Probably. Exist. Okay, and just to be consistent with our stuff that we wrote in the theorem, let's call the supremum M and let's call the infimum L. Okay. All right, so what does this mean? Well, remember from a proposition that we looked at a while ago, it's proposition 3.29 in Cummings, that if we have a bounded set, that there exists a sequence that is converging to the supremum and the infimum. Okay, so let's write that down. Okay, so this is in Cummings, and I know I called it something different in my notes, but let's just say this is proposition 3.29 in Cummings. This is on page 93. So there exists a sequence in this image converging to the supremum, and there's another sequence in this image converging to the infimum. All right. So what do we know about compact sets? We know that they're closed and bounded, right? And what do we know about closed sets? We know from chapter 5 that closed sets contain all of their limit points, right? And so L and M are limit points, right? They're limits of sequences in the set. Okay, that's, the intuitive idea of what a limit point is. And so let's write what I just said down. So by theorem 5.10 from Cummings, this is on page 154. A set is closed if and only if it contains all of its limit points. Well, since f of a, since the image under f is compact, that means it's closed, just by definition. Is closed. So f of a contains all of its limit points. And L and M are limit points. So the image contains L and M. So what does it mean to be, so for L and M to be in the image, what does that mean? That means that there's something in the pre-image so that when you apply F to it, you get L and M. So that's exactly what we're trying to show. There's some A1, A2 in the pre-image for which f of A1 equals M and f of A2 equals L. And we're done. So we have just shown that there's going to be something in A, in this compact A, so that when I apply F to it, I get the supremum and the infimum. And that's exactly what our extreme value theorem says. Okay, so let's look at some examples here. So by the extreme value theorem, we have a compact set A, right? Closed and bounded is compact. So -2 to 1, and our function is going to be defined by x squared. And so what the extreme value theorem says is that this function should achieve its supremum and infimum since A is compact. So if we draw a picture, so here we're going from -2 to 1, and -2 squared is 4, so that's that, and then that's going to be 1, this is going to be 0, 1 is going to be 1. So I don't know, bad picture, I know, but you know. So that's the function, that's the image under f of A. Okay, so that's my image. And so the extreme value theorem says, hey, since A is compact, it's going to achieve all those points. And indeed, it does. This guy right here is my sup, right? It's the largest point on my graph. And this guy right here is the inf. And we can see that f of -2 indeed equals 4. So that's achieved, right? There's -2 is indeed an A. So that's achieved. And then f of 0 is also, so 0 is an A, and so f of 0 is 0, and that's achieved. So by the extreme value theorem, our supremum and our infimum are attained. Okay, but here, not, because we have an open interval from -2 to 1, and if we look at the same picture, so here's -2, this is going to be 4, but with an open circle because we're not including -2 in our set. Okay, and so here's 1, here's 0, and then here's 1 again. So here is my picture again. Again, this is going to be the infimum, and that is attained, but the supremum is not attained. In other words, there is no x in -2, 1 for which f of x equals 4. Okay, and the extreme value can't guarantee that we will find something because the set is not compact. It's not closed. It's bounded, it's not closed. But yeah. Okay, so our next really nice result is the intermediate value theorem. Okay, so if we have a continuous function on a compact interval from a to b, and alpha is any number between f of a and f of b, then there's some c in the open interval from a to b for which f of c is equal to alpha. So before we get into the proof, let's look at a picture. Okay, so let's just look at a picture of what's going on here, what this thing is saying. So here we have the compact interval from a to b, and let's say that f of a is maybe right here, and then f of b is right here. Okay, so let's draw this on our axis. This is f of a, and this is f of b. Okay, and so we're assuming that alpha is some number between f of a and f of b. So let's say it's maybe right here. So here's alpha. And what the intermediate value theorem is saying is that there's some c in between a and b for which f of c equals alpha. And we can see that this is true from the picture that we've drawn. Our little c is going to be right here. And so this is our f of c. Okay, so how are we going to prove this? Well, let's go ahead and suppose without loss of generality that f of a is less than alpha and is less than f of b. Now, if this were not, if I had f of a was actually higher than f of b, you could apply a symmetrical argument. But just for the sake of time and whatever, to get the point across, we're just going to do this case right here. Okay, so now I'm going to define a set. So I'm going to let the set A be defined as follows. I'm going to say A is going to be all of the x in the interval a to b, so that f of x is less than alpha. Okay, and so what does this look like in the picture? So f of x has got to be less than alpha, so it's going to be all of this stuff, right? And so it's going to be all of these x's is going to be my a. This is a. All right, so we're going to define our set A like that. And note that A is bounded above by B. Right? X has to be in this closed interval from A to B, so X can't be larger than B. Now, and it can't be smaller than A as well. Let's write that. And bounded below by A. Well, what do we know about bounded sets? We know that they have supremums and infimums. Okay, so note that, well, maybe I won't say note again, but I'll say by completeness, it follows that A has a supremum. Okay, so there's like a maximum value in this set. Well, I shouldn't say maximum because it might not attain the maximum value, but supremum. Okay, so least upper bound. Let's call it M. Okay, and so we claim that when we apply F to that supremum of the set, we're going to get alpha. Okay, and that's gonna prove our claim, right? Because what was our claim? Our claim was that there was some something in between A and B. That's gonna be our M here. So this is like our capital M that lives between A and B, so that when you apply F to it, you get alpha. Okay, so that's our claim. And so let's show this by doing the less than or equal and greater than or equal to trick. So we want to show first that f of m is less than or equal to alpha. Okay. And so we know that our set A is bounded. And again, using that proposition 3.29 in Cummings that we used in a previous proof here, there's some sequence that converges to our supremum. Okay, that's in A. Okay, so by proposition 3.29 in Cummings, there exists a sequence in A, say A(n), so that it converges to the supremum. Well, what do we know? What do we know? We know that f was assumed to be continuous. We know some things about continuous functions in terms of sequences by the very first theorem of the lecture. What do we know? We know that if we have a sequence converging to C, if our function is continuous at C, and we have a sequence converging to C, then the sequence formed by applying f to that sequence is going to converge, right? Okay, so let's write that down. So we have the sequence converging to M, and since f is continuous, by theorem 6.4, this implies that f of an is going to converge to f of m. Okay? And since each of our terms in our sequence are going to be in capital A, by definition of capital A, well, capital A is going to be all of the x's in this compact set from A to B, so that f of x is less than alpha. So since each of these pieces in our sequence is in A, when I apply f to those pieces, those are going to be less than alpha. Okay, so by definition of A, we have that f of an is going to be less than alpha, right? And so, by convergence, we're going to have the following. We're going to have f of m is going to be the limit as n goes to infinity, f of an. And it's not going to just be strictly less than alpha, because we're talking about limits here. It's going to be less than or equal to alpha. And let me draw a picture. So here's alpha. And we're taking the limit as n goes to infinity of the sequence. All right, so we're taking the limit as n goes to infinity f of an. And so the limit could be alpha. Even though it's not attaining the value at alpha, the limit could be alpha. Okay, so that's what the less than or equal to is for. And so we have one direction. We have that f of m is going to be less than or equal to alpha. Check. And now we have to go the other way. We have to show that the image of m under f is going to be greater than or equal to alpha as well. Okay, so let's show that. Let's show that the image greater than or equal to alpha. Okay, so this is our next step. Once we have this guy, we'll be done. Our proof will be done, because we'll have that the image, I shouldn't be saying the image, it's just a point, right? M is the supremum. So f of m is going to be equal to alpha. And we know that m is between a and b. Okay? All right. So note that m is not equal to b because, why is this? We have that f of m is less than or equal to alpha by what we just proved. But by assumption, we have that f of b is greater than alpha, right? That was our very basic assumption, that f of b was greater than alpha. So we must have m is less than b, right? It can't be greater than b because we have these two inequalities and there would be a contradiction. Okay, so m must be less than b. All right, so it's not equal to b. So now we can consider a sequence. So consider the sequence Sm, Sn defined by m plus 1 over n. And let's think about, where this sequence lives for large n, okay? So for large n, this sequence is going to be in our set from A to B, right? Because remember that m is the supremum of this set, and if I'm adding smaller and smaller things when n gets really large, that's going to be contained in the set, right? We're not going to be somewhere over here when n gets large, okay? So we're just looking at long-term behavior of the sequence when n gets really large. M plus 1 over n is going to converge to m. Okay, so that sequence is going to be in our compact interval from A to B when n gets large. Notice that for each n in the naturals, this is going to imply that S sub n is larger than m, the supremum of A. So what does that mean? So what does this mean? For each n, m plus 1 over n is going to be larger than m. That's true, right? Because n is a natural number. Add 1 to it, add 1/2 to it. It's always going to be bigger than m itself. So what does this mean? Well, it means that Sn is not going to be in the set A, right? Right? Because what was the set A? The set A was all x in the interval from A to B, so that f of x was less than alpha. But here, m is the supremum, and so S sub n is always going to be outside of the set. Okay, so S sub n will be larger than the supremum, so S sub n is not going to be in A. So let's write that down. Is not in A. And so what is the definition of A? Well, the definition of A, again, is all x in this compact interval, so that f of x is less than alpha. So if S sub n is not in this set, that means that f of Sn is going to be bigger than or equal to alpha, right? If it were in the set, it would be less than alpha. But S sub n is not in the set, so f S sub n is going to be bigger than or equal to alpha. And since our sequence converges to m, and f is continuous, this means that f of s sub n is going to converge to s sub n. And therefore, f of m is greater than or equal to alpha. And so we have both directions. We have that f of m is less than or equal to alpha and that it's greater than or equal to alpha. So f of m is equal to alpha, and this proves the intermediate value theorem. So let's do some examples where we can actually apply the intermediate value theorem to some problems. So we want to use the intermediate value theorem, IVT, to show that x to the fourth plus x equals 3 has at least one solution on 1, 2. Okay, so here's our answer. We're going to let our function equal x to the fourth plus x. So suppose f of x is equal to x to the 4 plus x. And note, we already proved that any kind of polynomial in this form is continuous on all real numbers. So in particular, it's continuous on this closed interval from 1 to 2. All right, and so let's draw a picture so that we can apply our intermediate value theorem. And I don't know what this function really looks like. I don't care. I'm just going to draw a picture here. Here is our AB from our theorem. So 1 to 2. So what are we trying to show? We're trying to show that f of x equals 3 has a solution in 1, 2. All right, we called this f of x. So f of x equals 3 has a solution on 1, 2. That's what we're trying to show. Okay. So we're going to use the intermediate value theorem. We're going to look at the endpoints, f of 1. So if I plug in 1 to my f function, I get 1. No, I don't. I get 2. And then if I plug in 2 into my f function, I'm going to get, well, 2 to the 4th plus 2 is going to be 18. So let's go ahead and graph it. So here's f of 1 is going to be 2, and f of 2 is going to be 18. Let's see. I'll put 18 right here. This is 18. This is 2. Let's say it's right here. And so where's 3 at? Well, 3 is like right here. And so by the intermediate value theorem, since 3 is between f of 1 and f of 2, we know that there's some c here such that f of c equals 3. Okay, and that's what we're trying to that's what we were trying to show, that f of x equals 3 does have a solution in 1, 2. Okay, so yeah, I don't know. Let's say it's like right here. Okay, so here's my f of 3. So that guy is between f of 1 and f of 2. And so this is going to be c. So we conclude by the intermediate value theorem that there exists a c in 1, 2 so that f of c equals 3. So indeed, this guy does have a solution on 1, 2 because this guy, f of x equals 3, has a solution in 1, 2. And we used the intermediate value theorem to conclude that. All right, so let's do one more application of the intermediate value theorem. We're going to play the same kind of game here. We want to show that sine of x equals x has a solution in the real numbers. And so our steps here, we're going to say that sine of x equals x has a solution, so there's some x that satisfies this, if and only if there exists an x for which, if I subtract x on both sides, sine of x minus x equals 0, right? So we'll let our function f of x be sine of x minus x, and we claim that there's some x for which f of x is 0. Okay, so that's our claim here, right? It's just saying the exact same thing as sine x minus x equals 0 has a solution. There's some x for which f of x is equal to 0. All right, so we're going to use the intermediate value theorem to show that, you know, we're going to pick a negative number and a positive number and show that solutions exist there, and deduce that by the intermediate value theorem, there has to be, like, it has to cross the x-axis. So let's draw the picture. So the picture here, and again, this is not going to be a great picture, but the idea here is we're going to look at negative pi over 2, and then we'll look at positive pi over 2. Okay. Actually, that's not what I wanted to do. Let me change this. Sorry, guys. Let's relabel this. I meant to say f of negative pi over 2, and then this is going to be f of pi over 2. And we can see that 0 is going to be between those guys, and so by intermediate value theorem, it has to have a solution. Now, let's actually prove that I drew this picture right. And actually, I drew it backwards. This is going to be negative pi over 2, and this is going to be positive pi over 2. So f of negative pi over 2 is going to be sine of negative pi over 2 plus pi over 2. And if you check in your calculator, this number is positive. It's going to be greater than 0. So it is going to be up here. And then if you check in your calculator, f of pi over 2, sine of pi over 2 plus pi over 2 is going to be, I meant minus, I meant minus pi over 2. Because this is a double negative here. This is minus pi over 2. That's why I wrote that. So this is going to be minus pi over 2. And this is going to be a negative number. So the picture should look okay. So by the intermediate value theorem, since 0 is our alpha, there's going to be, by IVT, there exists, and maybe I should extend out my line here. So this is going to be negative pi over 2 right here. And I'll draw this as pi over 2 right here. So there's going to be some c that achieves 0. So like, let's say that this is going to be, let's say that this is right here, okay? And so at pi over 2, I'm going to be down here. And so by the intermediate value theorem, I have to cross 0 somehow to get to f of pi over 2. There exists c in negative pi over 2 to pi over 2. And it might not be c equals 0. It's just the way I drew the picture. Thus, sine x equals x has a solution on the reals, and in particular in negative pi over 2 to pi over 2. Okay, so that is our video this week. Thanks for watching, and I will see you guys next time. We're going to talk a little bit about uniform continuity, and then we're going to get into derivatives. Okay, so thanks for watching, and see you then.